Well, hello again. In this example, you'll learn how to incorporate support settlement within the flexibility formulation. We will specifically be looking at this particular beam that has the following support reactions: reaction at 1, moment at 1, reaction at 2, reaction at 3, and moment at 3. The problem that arises is that the total number of unknown forces that we have in this case is 5, and yet the number of equilibrium equations that we have is only 2. And the reason that is the case is that we are neglecting axial for this consideration. You'll notice I don't have reactions in the x direction, and I'm not going to use a summation of forces in the x direction either. So that means that I am 5 minus 2, which then says I am statically indeterminate to the third degree. And that says then that I need 3 redundant reactions to be able to select. The problem statement here tells me that I'm going to choose moments at 1 and 3 and the reaction at 2 as my redundants. But to complicate matters just a little bit, we notice the beam experiences a settlement of ½ inch in the downward direction at support 2. So we are going to want to incorporate that into our flexibility formulation as we move forward here. So the first thing we do is we remove those 3 redundant reactions, and that gives us our primary structure. And then I'll sketch the deflected shape for this, and I get a rotation at 1, displacement at 2, rotation at 3, and you'll notice that those are the locations where the redundant forces had been previously. That is why we chose that location. Then I begin the process of applying my redundant forces back on to my separate structures, my redundant structures. And I get, in this case, rotation at 1 due to a moment at 1, displacement at 2 due to a moment at 1, rotation at 3 due to a moment at 1. And those can also be rewritten in terms of their flexibility coefficients, F31 times M1, and so forth. And we can go ahead and take a look at that in a similar fashion for the other 2 redundant structures, where I've got the force applied here, and then I've got the moment applied here. All of this is typical in the process for dealing with indeterminate structures using the flexibility approach. We are trying to incorporate settlement, and where that comes into play is in the generation of the compatibility equations. Since I had 3 redundant forces, I need 3 compatibility equations. And the way those are developed is we will come back here to our 4 structures, the 1 primary structure and the 3 redundant structures, and we will sum up all the rotations that occur at a particular location, or all the displacements that occur at a particular location. So let's look at the first one here. We would get theta 1 plus F11 M1 plus F12 R2 plus F13 M3, and all of that has got to be equal to 0 because we know in the real structure that there is a 0 rotation at that particular location. Now for summing up the displacements at point 2, and all of that is equal to the quantity that we know for this particular location right here. Now, under normal circumstances, we know that that displacement there would be 0, but in this particular situation, we know that there's an actual settlement that occurs at that location. And so the compatibility equation must acknowledge that and indicate that we are moving in a downward direction of 0.5 inches. So that's negative 0.5 inches. For the location of the third support, I can go ahead and get that compatibility equation put together. And you will notice that that is equal to 0 in that particular case, because in the real structure, the rotation there is indeed 0. I can then take these expressions and I can write them in matrix form. And what I'm going to do is I'm going to take these rotations and displacements, I'm going to move them to the other side of the equation, so we'll get some negatives. And that is where this vector comes into play. So I had 0 minus a theta 1, and then I have that negative ½ of an inch minus delta 2, and so forth. And then I get a matrix here of the flexibility coefficients and a vector here of the unknown redundant forces. So the solution to this actually requires me to compute some rotations and deflections on my primary structure and also some rotations and deflections on my flexibility structures, as we see here. Now recall that the flexibility structure is the situation where we apply unit moments or unit forces at the locations of my redundant forces. And it produces deflected shapes like this, where the flexibility coefficients are displacements due to applied unit forces or unit moments. So the task really now becomes in computing what those unknown displacements are, both for the primary structure and for the flexibility structures. And in this particular case, we can use beam charts to our advantage. We would then have a simple supported beam that has a length equal to 420 inches long with a distributed load of 1/6 kips per inch. And what we're trying to do here is make sure that we get a consistent set of units as we move forward in our calculations. We are also going to be interested in knowing a deflection out here, that's that delta 2, at a distance where x is equal to 180 inches. And so you'll notice that playing into some of our calculations down here. We will be interested in knowing the rotation at these two locations as well. And if you look, you can see where those quantities come into play. For the flexibility structures, we would come in here and we would apply that unit moment, and we would then compute using the equations for deflection and rotation that we have as well. Please pay attention to the units here for flexibility coefficients. What it simply says is that this is the rotation that is due to a unit moment, the displacement that is due to a unit moment. And as we proceed forth and we give our unit force here and we calculate what these quantities are, look at the units: rotation due to a unit force, displacement due to a unit force, and so on. And so recognizing then Maxwell's theorem of reciprocity, we recognize that F32 is equal to F23, and that helps me to get these flexibility coefficients just a little bit faster. I can then drop these into the matrix formulation, and you'll notice here this is where that known settlement is showing up. All these other things are coming from the beam charts, as we'd previously gotten, and we are looking for these unknown redundant forces. We can solve for those redundant forces by taking the flexibility matrix and moving it to the other side, and that we do that by taking its inverse. And we plug in all the known quantities in here and known quantities here. I did actually give the quantity here for you to see because I wanted you to see where that was coming from explicitly due to that support settlement that we were dealing with. And if we do that calculation, we can get the following quantities: 2,240 kip inches, 3.6 kips, negative 2,294 kip inches. Alright, so we can go ahead and transfer these over to our diagram. 2240, 2294, and this 3.6 kips. I can then get the reactions at 1 and 3 by taking equilibrium. Here's the resultant force of 70 kips, and that is over here a distance of 210 inches. And these are my two equilibrium equations that I could then solve for the remaining unknowns. That concludes this example. As always, it's a beautiful day for studying structures.